Present day, a museum collection room. Fluorescent lights flicker against tall steel cabinets. A heavy metal drawer slides open. Inside, resting on archival foam, lies a single massive tooth. It is heavy, dark, and serrated. For decades, popular culture has imagined the creatures that left these teeth as tireless movie monsters. They are depicted as unassailable terrors. But the fossil record does not preserve monsters. It preserves biological machines. Late Cretaceous, about 70 million years ago. A heavy-bodied predator steps through dense ferns. Its massive frame requires extraordinary energy just to remain standing. Every step carries a metabolic cost. That cost must be repaid in flesh. When we strip away the Hollywood myths, what were the true biological limits of the largest predators on Earth? To find out, we must look for the moments when their biology failed. We look at the damage. Late Cretaceous, about 70 million years ago. In what is now Madagascar. The landscape here is preserved in the rock layers of the Mapusaurus Formation. It was an environment defined by punishing seasonal extremes. For months at a time, the rains simply stopped. Rivers dried into shallow, muddy pools. Surrounding vegetation withered under a relentless sun. Starvation was a constant threat. To survive here required extreme adaptations. In this brutal biome, one predator dominated. It was Majungasaurus. Reconstruction, constrained by its skeletal anatomy. We picture a creature with a short, blunt snout. A single, small horn rested on its head. Its legs were unusually short and stocky for a theropod of its size. It was not built to chase prey over long distances. Instead, it was an ambush hunter. It waited for desperate herbivores to gather around the shrinking watering holes. But when the droughts stretched on, the herbivores died. The food web collapsed. Present day, a paleontology preparation lab. The air hums from an extraction fan. A researcher sits at a wooden bench under a bright desk lamp. They examine a fossilized rib bone retrieved from the Mapusaurus Formation. This bone belongs to a Majungasaurus. But the surface of this rib is not smooth. It is marred by deep, parallel gouges cutting into the outer layer. These are bite marks. To understand what happened, we must measure the damage. The researcher picks up digital metal calipers. They carefully align the steel tips with the deepest part of the parallel grooves. Precision is absolutely critical here. The calipers read the distance between the individual scratch marks. The screen displays exactly 21 millimeters. This spacing is not random. It is a forensic signature. It was left by the serrations of a specific tooth dragging across the bone. This measurement allows paleontologists to narrow down the suspects. They compare the 21 mm spacing to the jaws of known carnivores from this rock layer. There is only one match. The dentical spacing and jaw curvature align closely with the teeth of Majungasaurus. The gouges were made by another Majungasaurus. This apex predator was stripping the meat from the bones of its own kind. SRC01, Nature. 2003-2007. We can't tell if the animal was killed in a fight or merely scavenged from this evidence alone. What it does support is that Majungasaurus fed on its own species. This is cannibalism. Reconstruction, constrained by the taphonomy of the site. We envision a starving predator finding the carcass of a rival. As drought ravages the ecosystem, biological drive overrides all other instincts. The predator anchors its heavy legs, latches its blunt jaws onto the rib cage, and pulls. It strips the carcass to stay alive. The myth of the proud, solitary hunter dissolves. In its place, we find a desperate biological machine doing whatever it takes to survive. SRC01, Nature. 2003-2007, present day, a paleontology excavation quarry. Mud sticks to the boots of field workers as they stretch bright white string across an open pit. They are laying down a taphonomic grid. Every bone pulled from the dirt receives a precise GPS coordinate. A solitary fossil tells us only that an animal died. The context is everything. By mapping the exact placement of multiple fossils in 3 dimensions, scientists read the history of the ground. Here in Argentina, the rock belongs to the Huincal Formation. This grid covers an extraordinary concentration of predatory dinosaurs. The quarry is packed with the remains of Mapusaurus. Mapusaurus was a giant carcharodontosaurid. This massive meat-eater shared its environment with some of the largest long-necked sauropods to ever live. Finding several of these predators buried together immediately sparks a compelling narrative. It is easy to imagine a coordinated, military-style pack hunting down a titan on the order of a city buzz. But one study's taphonomic interpretation suggests a much darker reality. When the vertical placement of the bones is mapped, they are not found on a single flat plane. They are scattered across multiple distinct sediment layers. SRC03, Geodiversitas. 2006. This vertical spread indicates that these predators did not die in a single catastrophic event. Instead, the bones accumulated slowly. They gathered over seasons, or perhaps decades. The site was likely a predator trap, drawn by the smell of a mired carcass. Successive waves of predators arrived. They fed, and sometimes died in the mud themselves. We can't tell if they communicated to coordinate a hunt from this evidence. What it does support is a chaotic feeding aggregation at a predator trap. The evidence forces a complete reframe. SRC03, Geodiversitas. 2006. To understand how these aggregations worked, researchers looked at living archosaurs. Modern crocodilians do not hunt in highly organized packs led by an alpha. They simply swarm. When a large food source becomes available, individuals arrive independently. They aggressively compete for the best pieces of meat. It is a violent, uncoordinated mob. Based on modern archosaurs, researchers argue that this mobbing model better fits the fossil record of grouped theropods. SRC04, Bulletin of the Peabody Museum of Natural History. 2007, Late Cretaceous, about 95 million years ago. A massive sauropod carcass rots in a muddy depression. Reconstruction, constrained by taphonomic distribution. We picture several Mapusaurus converging on the kill. It is a frantic, unthinking desperation to eat. The predators do not cooperate. In the chaos of the feeding frenzy, they slash and bite at one another. Smaller individuals are trampled into the mud. The popular image of the calculating raptor pack fades away. It is replaced by a highly dangerous, competitive mobbing event. The predators are just as likely to maim each other as they are to kill their prey. SRC04, Bulletin of the Peabody Museum of Natural History. 2007, Late Cretaceous, about 70 million years ago. In the rock layers of South America, we find evidence of predators securing meals in new ways. Another lineage, known as the megaraptorids, roam this continent. A primary example is macrothorax. Anatomical proportions indicate a radical evolutionary shift in this family. Their skulls became lighter and narrower. They abandoned the heavy bone-crushing power of their ancestors. Instead, they weaponized their arms. SRC08, Scientific Reports. 2022, Reconstruction, constrained by the massive fall-in bones recovered from the rock. We see Mipe utilizing a completely different hunting toolkit. While its jaw was relatively weak, its chest was broad and powerful. This structure anchored massive arm muscles. The predator reached out with deeply curved talons to hook and hold its target. The jaws were secondary. The arms did the heavy lifting. By shifting the biomechanical load away from the skull, megaraptorids partitioned the ecosystem. They carved out a new biological niche. Yet, in North America, a different group of predators doubled down on the power of the face. SRC08, Scientific Reports. 2022. Present day, a preparation lab. The rhythmic hum of machinery vibrates through the room. A researcher operates a handheld 3D laser scanner. Bright red beams sweep across a massive, gnarly skull resting on a steel table. The digital map appears on a nearby monitor. It builds a high-resolution model of the bone's surface. This is the skull of Dinosaurus. It was a heavy-built tyrannosaurid that lived about 10 million years before Tyrannosaurus rex. It is an impressive specimen. But it is not pristine. The surface of the snout and jaw is broken by deep, circular gouges. Late Cretaceous, about 75 million years ago. The Dinosaur Park Formation in North America was a lush, subtropical floodplain. Forests of conifers and ferns crowded the banks of shifting river channels. It was an ecosystem packed with massive horned and armored herbivores. Every meal required raw, overwhelming force. Dinosaurus was the apex predator here. Its skull was heavily reinforced to absorb massive impact forces. But the deepest scars found on these skulls were not inflicted by their prey. The laser scanner highlights a massive puncture wound on the maxilla, the upper jaw. It is a violent injury that broke straight through the solid bone. But crucially, the edges of the bone around the puncture are not sharp or splintered. They are smooth and swollen. This is bone remodeling. The physical evidence of osteoblastic healing proves the animal lived long after the attack. It walked around for years with open, festering wounds on its face. These eventually calcified into thick, gnarled scars. SRC02, page 2015. To find the culprit, researchers look at the shape of the damage. The deep, conical punctures closely match the heavy, rounded teeth of another tyrannosaur. The prevalence of these scars across multiple specimens suggests a pattern of behavioral combat. These animals were biting each other directly on the face. We can't tell if the combat was over territory or mates from this evidence alone. What it does support is that the Dinosaurus survived a massive face bite from its own kind. SRC02, page 2015. Reconstruction, constrained by the pathology on the bone. We picture two Dinosaurus squaring off in a dense forest clearing. The combat is not a precise, tactical strike. It is a brutal, clumsy collision of mass. The heavy jaws lock onto the snout of the rival. Teeth punch straight through the skin and anchor into the skull. The animals thrash violently. They rip away chunks of flesh and bone before separating. It is a life cycle of systemic violence. The scars reveal a profound truth about the life of an apex predator. They did not live unassailable, untouchable lives. They were biological machines constantly operating at the edge of physical failure. They survived terrible injuries, healed, and continued to hunt with compromised bodies. A giant theropod was a walking testament to endurance. Millions of years later, this evolutionary arms race would produce a skull capable of generating forces unlike anything else on land present day, a biomechanics laboratory. A computer monitor displays a brightly colored wireframe model of a massive skull. The jaw hinges and teeth glow a deep red and yellow. The upper snout fades into cool blues. This is a finite element analysis heat map. It simulates physical stress. The skull belongs to Tyrannosaurus rex. For decades, popular culture has debated how this massive predator hunted. By testing the physical limits of the skull, science provides a deeply unsettling answer. Before we look at the tyrant king, we must understand the predators that came before it. In South America, giant carcharodontosaurids like Mapusaurus and Giganotosaurus ruled the floodplains. Popular myth suggests that these giants took bites out of living, mountain-sized sauropods and simply waited. This flesh-grazing myth borrows from outdated theories about modern Komodo dragons. The jaws tell a different story. Carcharodontosaurid teeth were relatively thin and bladed. They were lined with microscopic serrations like a steak knife. These jaws were engineered to slice cleanly through thick hide and muscle. They caused rapid, catastrophic blood loss. They were surgical weapons. But the skull of Tyrannosaurus rex was not built for surgery. It was built for demolition. Late Cretaceous, about 68 million years ago. The Hell Creek Formation in North America was a coastal environment of swamps and dense forests. Here, Tyrannosaurus rex dominated the landscape. Its teeth were not thin, serrated blades. They were thick and round. When a Tyrannosaurus bit down, the robust architecture of the skull absorbed massive shockwaves. This prevented the bone from shattering under its own power. Biomechanical models remain debated, but one study estimates the bite force reached roughly 60.000 newtons. SRC-07, Nature. 1996. We can't tell the exact muscle volume from this evidence. What it does support is that the skull architecture was reinforced to withstand 60.000 newtons of force. This is roughly the pressure required to crush a small car. The jaws did not slice. They exploded bone into shrapnel. When a Tyrannosaurus bit a Triceratops, it shattered the ribs and pulverized the internal organs. This allowed the predator to consume the entire animal. Hide, meat, and bone. SRC-07, Nature. 1996. Reconstruction, constrained by these biomechanical models. We see Tyrannosaurus rex acting as a biological wrecking ball. It does not need to gracefully outmaneuver its prey. It relies on overwhelming force. It is the ultimate expression of the heavy-skulled terrestrial predator. But while tyrannosaurs maximized the power of their jaws on land, another lineage of giant theropods was abandoning the dry earth. They evolved to dominate an entirely different extreme. Present day, a histology lab. The screech of a diamond-edged rock saw fills the room. A technician wearing safety goggles guides a section of fossilized bone into the spinning blade. Dust and coolant water kick up. The saw cuts a microscopic sliver from a heavy femur. The fossil is polished down until light can pass straight through it. The slide is placed under a polarized light microscope. The glowing structures on the monitor will force a radical rewrite of dinosaur ecology. Late Cretaceous, about 95 million years ago. The landscape of North Africa, preserved in the Kemkem beds, was a massive waterway system. Broad rivers snaked through mangrove-like swamps. It was an ecosystem overflowing with life. But it was dangerously unbalanced. The fossil record here is completely saturated with the remains of giant predators, with relatively few large land-dwelling herbivores to support them. In an environment with too many mouths and not enough terrestrial meat, competition forces evolution to find a new path. The bone on the microscope slide belongs to Spinosaurus. When we look at the cross-section of a typical theropod dinosaur, like a T-Rex, we see a hollow core. Theropod bones were generally light and air-filled. This is an evolutionary trait shared with their modern bird descendants. But the slide on the monitor shows something completely different. The bone of the Spinosaurus has almost no hollow space. It is incredibly dense and solid all the way through. This condition is called osteosclerosis. It indicates that this animal carried massive internal weight. SRC-05, Science. 2014. This density suggests a function similar to modern hippopotamuses or penguins. The heavy bones acted as aquatic ballast. They prevented the massive dinosaur from bobbing to the surface like a cork. This allowed it to sink into the water column. The physical density of the bone pivots our understanding of this creature away from the dry land. It pushes them directly into the rivers. SRC-05, Science. 2014. We can't tell the exact swimming stroke from this evidence. What it does support is that the Spinosaurus functioned as dense aquatic ballast. The exact mechanics remain intensely debated. While one model proposes a highly aquatic pursuit lifestyle powered by massive tail thrust, other biomechanists strongly contest this. They suggest the animal was too buoyant for agile swimming. They argue instead that it acted like a giant wading heron. It anchored against strong river currents. Here, it waited. SRC-05, Science. 2014. Late Cretaceous, about 95 million years ago. Reconstruction, constrained by its dense histology. We see Spinosaurus utilizing the chem waterways. It is a highly specialized predator that partitioned the ecosystem. By exploiting the rich aquatic food web, it avoids direct competition with the other giant carnivores hunting on the muddy banks. It is a masterclass in evolutionary adaptation. The giant theropods were deeply tied to the environments that shaped them. They required heat. They needed massive amounts of food and liquid water. For over a century, the scientific consensus held that dinosaurs were effectively giant, cold-blooded tropical reptiles. They were thought to be completely incapable of surviving sustained freezing temperatures. But a completely different extreme awaited in the north present day, a field site in northern Alaska. Paleontologists in heavy jackets stand near a freezing stream. They load buckets of mud from the Prince Creek Formation into metal micromesh screens. Freezing water washes away the silt. It leaves behind tiny pebbles and fragments of bone. A researcher wearing thick gloves uses tweezers to pick out a tiny, sharp tooth. It is no larger than a grain of rice. Finding fossils up here is miserable work. But these fragments shatter a paradigm. Late Cretaceous, about 69 million years ago. The North Pole was not covered in a permanent ice cap. But it was far from tropical. It was a dense, high-latitude forest of conifers and ferns. The environment experienced punishing seasonal shifts. Every winter, the region plunged into total darkness. For roughly 120 days, the sun never rose. Icy winds scoured the landscape. Temperatures dropped below freezing. Snow blanketed the ferns. For decades, researchers assumed dinosaurs migrated thousands of miles south before the cold set in. The micromesh screens challenge that theory. The tiny fragments pulled from the Alaskan mud belonged to neonates. They were hatchling dinosaurs just out of the egg. Researchers find the tiny bones of the herbivore Mapusaurus. They find the tiny teeth of a small predator, Troodon. The presence of neonate bones strongly infers year-round residency. A baby dinosaur could not possibly migrate thousands of miles before winter arrived. The babies stayed in the north. This means the adults stayed. 2. SRC06, +1. 2014. We can't tell the exact thickness of their feathers from this evidence. What it does support is a warm-blooded metabolism capable of surviving polar winters. Surviving these extreme, dark months required a metabolism operating far above that of modern reptiles. It required endothermy. The dinosaurs were generating their own body heat. They pushed the limits of biology to conquer the freezing dark. SRC06, +1. 2014, Late Cretaceous, about 69 million years ago. The long polar night has set in. Reconstruction, constrained by the microfossil evidence. We picture the dark, snow-covered forest. A predator moves silently through the trees. This is Majungasaurus. It is a northern relative of the Tyrannosaurus. While initial estimates suggested a dwarf species, ongoing discoveries argue for a much larger predator. It is a massive, warm-blooded machine. It is likely wrapped in a dense coat of insulating feathers. These trap the heat generated by its high-revving metabolism. Majungasaurus stalks the overwintering herds. It is joined in the dark by Troodon. The sheer size of the orbital cavities in the skull of Troodon implies enhanced vision. This allowed it to navigate and hunt in the near-total darkness of the polar night. The cinematic image of a sluggish, cold-blooded reptile is completely dead. Here in the freezing dark, the biological machine is running hot. It is fast, adaptable, and perfectly tuned to survive the harshest environment on Earth. Late Cretaceous, about 66 million years ago. A massive asteroid strikes the Earth. It brings the reign of the giant apex predators to a sudden and catastrophic end. These biological machines had mastered every extreme environment on the planet. From the drought-stricken plains of Madagascar to the freezing darkness of the Arctic. Now, they are dismantled. Reconstruction, constrained by the global fossil record. We picture the silence that follows. The giant skulls, slicing teeth, heavy aquatic bones, and winter plumage are buried in the mud and ash. When we strip away the Hollywood myths, what were the true biological limits of the largest predators on Earth? They were not calculating monsters or unassailable titans. They were highly specialized, intensely vulnerable animals. They lived lives defined by scarcity and systemic violence. They faced the crushing metabolic demands of their own massive bodies. They scavenged their own dead. They maimed each other in frantic feeding mobs. They walked around with festering, shattered faces. They evolved incredible adaptations to squeeze life out of swamps and snow. Present day, a museum collection room. The metal drawer remains open. The heavy, serrated tooth of Majungasaurus rests on the foam. It sits alongside a scarred Dinosaurus skull and a tiny toe bone from the Arctic. The physical evidence is here. It is measured in calipers, laser scans, and rock saws. The fossils preserve the architecture of life. They map the ultimate limits of endurance. But the spaces between the bones remain lost to the dark. We cannot hear the rivers or see the exact colors. The thoughts behind the massive jaws are gone.